geometry students. Welcome to week 28. The good news is this week's homework was a lot shorter than last week's homework was. I know that was a little bit rough, but I really wanted to have a really thorough review assignment so everybody would be ready for the chapter 11 test. So hopefully you're watching this, spring break is done, your brain is all refreshed, and you're ready to pound it out these last 5 weeks. So anyway, these are the geometry students. I don't know if you can see my shirt or not, but this is some of the terms you may not know to Algebra 2, but see if you can figure out what the top sentence says. If you have older siblings or really gung-ho mathy parents, they may be able to help you out with it. Anyway, there's only 2 sections this week. It is 12.1 and 12.2, so let's get started. I don't have a videographer, so there's always a little bit of a time delay. The only reason the writing is on that paper is I was having a hard time getting it to focus. So I was practicing. Okay, so we're starting a new chapter. So I want everybody to open your book to the beginning of chapter 12. And this will be on page 762. So I want to talk through some definitions and stuff first before we jump into the problems. 12.1 is not too bad. 12.2 is one of my least favorite sections in this chapter. As I promised you guys, chapter 12 is going to be easier than 10 and 11 were. I think they know everyone's kind of brain dead after spring break, so they kind of take that into account. So first of all, we're going to talk about the word tangent. And tangent actually doesn't mean anything like what it meant when we were doing it for circles. Actually, it does a little bit, but not enough to make sense for you guys. So I want you to rethink about your definition of tangent based on what we learned in our trig chapter in chapter 8. So the definition of a tangent to a circle. First of all, the word tangent, if it's used by itself, in this context, it'll always refer to a line or a line segment or a ray, but definitely a length. So a tangent to a circle is a line in the plane of the circle that intersects the circle at exactly one point. You'll see for line AB, if it was any closer in, it would cut through the circle. If it was any further out, it would miss the circle entirely. So a tangent line touches the circle at one and only one point. We'll learn what the other kinds of lines are called later. The point at which the circle, the surface of the circle and the tangent intersect is called the point of tangency. So line AB is tangent to the circle, ray BA is tangent to the circle, and line segment BA is tangent to the circle. Point B is the point of tangency. Okay? Okay. So this is the most important theorem that we're going to learn in this section. If a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So anywhere you would draw a tangent line, if you drew a line from the circle, from the center of the circle to the point of tangency, it will be a radius. Okay? This also kind of lines up. There's a converse of this one that I want to bring up now because I think they go together. So theorem 12.1 and theorem 12.2, this is the converse. If you have a line and it is perpendicular to the radius, then the line has to be tangent to the circle. So here's something kind of important to know. Just because a line looks tangent, you don't know that it's tangent. You would have to have that little square sign to show that it's perpendicular to prove tangency, or it would have to say tangency. Just because it looks tangent doesn't mean it is. Just like in the past, just because something looks like a right angle doesn't mean it is. So to go back to everybody's chapter 2 stuff favorite, we can actually turn this into a biconditional like we learned in chapter 2. So if a theorem and its converse are true, then we could write a biconditional saying a line is tangent to a circle if and only if the line is perpendicular to the radius at the point of tangency. So both of those are true. Okay, so let's use that to work some problems. So again, everybody should have your book out. And I want you to look at problem 1 on page 763. And that's not got it problem 1, that's just the regular problem 1. And you'll see the picture with quadrilateral M, L, O, and N. I'm not going to draw the circle, but I'm going to draw the rest of it. Looks something like that. And we know this angle is 117 degrees. And they want you to find the value of x. So first of all, this is a radius, and this is a radius. And they told us that ML is tangent and MN is tangent. And by theorem 12.1, we know that if we have a tangent line, if the tangent line is if the tangent line, and if something's a tangent line, then it's perpendicular to the radius. So since we know that's a tangent line and that's a radius, we can make that a right angle. And same thing here, since we know this is a tangent line and this is a radius, we know they have to be perpendicular by theorem 12.1. So that's one that kind of needs to be memorized. There will be no note card on this test, so that's one you'll have to know. Now you got to go back to what you know about quadrilaterals. This was from chapter 6. So this would have been at the end of the fall semester. The rule for quadrilaterals is all of the interior angles add up to, I'll let you fill in that blank. And if you want, you can just think about this like any rectangle or any square. All those that have to add up to 360 degrees, because if you think about it, a square is 4 right angles, 90 plus 90 plus 90 plus 90. Same thing for rectangles, so 360. So we know that, and they called it x. So I expect you to turn, even though it's not a formula problem, I expect you to do the number sentence and write it. So we know that 117 degrees plus 90 degrees plus 90 degrees plus x equal 360. We can combine some stuff. We know that 297 degrees plus x equal 360. Subtract 297 from both sides. And we know that x equal 63. So the measure of angle M equals 63 degrees. It's like I forgot some degree symbols there for a while. I better go back and put them in before I get myself in trouble. Okay? So that's how you do those. Those are pretty simple. It's just a question of remembering the rule about if you know that a line is tangent, it will always be perpendicular to the radius. And remembering that the sum of the angles in a quadrilateral equal 360. So if you remember those two rules, you can solve these type problems. Moving on. Okay. Okay, in order to do the next problem, you're going to have to make sure that you remember something from Algebra 1. And I know some of you guys aren't super strong on Algebra 1, so I'm going to do a quick review of this. And that's the concept of FOIL. FOIL is used when you're multiplying two binomials. So if you already remember this, you don't need to write it down. You may, if you don't, you may want to take notes. F stands for first. Can't spell first. Outer, inner, last. First, outer, inner, last. And what it is, it's a way of multiplying two binomials. And these are going to be more simple than most because our two binomials for what we're doing in this chapter will always be the same thing. So if you have something that looks like x plus 7 squared, you should rewrite it as, remember squared just means any number times itself. So x plus 7 times x plus 7. I'm going to copy it down here so you can see the FOIL easier. So we're going to do the first in each binomial. So this and this one are the first terms. And binomial just means two terms. So this is the first binomial. This is the second binomial. Okay, so the first terms in each binomial, x times x is x squared. Now we're going to do the two outer terms. So we're going to do x and positive 7. So 7 times x is 7x. Now we're going to do the inner ones, the inside ones. And 7 times x is 7x. And then we're going to do the last terms in each binomial. So this is the last one in the first binomial. This is the last one in the second binomial. Plus 49. The good thing about doing them in this order is you combine like terms. X squared plus 49, plus 14x plus 49. Okay, so typically anytime you, almost always, and definitely always in what we're doing in this chapter, anytime you multiply two binomials that are in this format, what's going to happen is you're going to end up with a trinomial because the two middle terms will combine. Okay, so now that we reviewed FOIL, this is going to be necessary as an intermediate step in one of our geometry problems. Okay, so I want you to look at the top of page 765. We're going to work problem 3, not got it problem 3. So I'm going to focus on this triangle. I'm not going to draw the circle as well. So we've got B, C, A. We know, actually I guess I do need the circle. Shoot. And we know the radius is X. And this 8, the way they drew it, what that means is the 8 is going from this tip to here. But we're going to focus on triangle ABC. Since it's a right triangle, we can do Pythagorean theorem. But for those of you that aren't great at your parentheses, and those of you that know it because I called it out on feedback on the 11 quiz, we want to make sure we're really careful with our parentheses in these. So we know Pythagorean theorem is a squared plus b squared equals c squared. And so a squared is going to be one of the legs, x squared, plus b squared. That's going to be the other leg. Here's where you have to be careful. The length of the hypotenuse from here to here is 8, from here to here is x. So the whole thing is x plus 8. You could write 8 plus x, but when you're doing FOIL, it's way better to do it this way. So this part will be easy. X squared plus 144. Now I'm wishing I'd done it over here because of what I taught you guys last week. But I'm going to do this over here, even though I should have done it over here. And anyway, so I'm going to recopy it twice. Okay? Now what I'm going to do is I'm going to do FOIL. X times x is x squared. Outer, 8 times x is 8x. Inner, 8 times x is 8x. And last, 8 times 8 is 64. Okay, equal x squared plus 16x plus 64. Now your first thought is, oh no, I'm going to have to do a quadratic. But here's the sweet thing about almost all of these problems, maybe even all of them. The x squared, we're just going to subtract it out. And we have 144 equals 16x plus 64. Again, the goal is to get the x by itself. So let's knock out. And we end up with 80 equals 16x. Divide both sides by 16. X equals 5. So the radius is 5. So that's how you solve these. The trick is to recognize the right triangle. Think, I've got one unknown and I've got 3 sides, so Pythagorean theorem should work. Remember how to get the length by adding 2 adjacent segments, and then make sure that you don't. Here's what's important to note. Here's what not to do. Hesitate to even write it down. Here's what you can't do for these. Because of that plus sign, or if there was a minus sign, here's what you cannot do. You can't distribute it and say x squared plus 64. That will give you the wrong answer. So if there's 2 terms inside the parentheses with a square, the only way to solve it is FOIL. You cannot just distribute that squared. Okay? That was probably the hardest one in this section. Okay. We're going to use the concept of the converse to do problem 17. So we're looking at problem number 17 on page 767. So everybody go to that page. Okay. And it says, determine whether a tangent is shown in each diagram. Explain. So you can't say that, oh, it's a right angle, because there's no right angle marking. You can't say it's a tangent, because remember what I said, you can't automatically assume it's a tangent just because it looks like it. But we know the converse says that if two lines are perpendicular, then the line is a tangent. We know 6 is a radius, and we don't know if that 8 line is a tangent or not. But we know that if, let me go ahead and draw it. But we know if we can prove that that angle is 90 degrees, if we can prove that it's a right angle, then that's enough with the converse theorem to say that this line is tangent. So the way we'll check it is we'll do Pythagorean theorem. So leg plus leg, leg squared plus leg squared equal hypotenuse squared. Actually, I probably should write the formula. Question mark. And the reason I put a question mark there is if it's true, then we know that this is a right angle. And if we know this is a right angle, we know this is tangent. If we work this out and it's not true, then we know that's not a right angle. Therefore, that can't be a tangent. Okay. 64 plus 36 equal 100. 100 equal 100. It checks. So the line is a tangent. Okay. And the last one, I can't do one of the homework problems because I assigned them all. So I want you to flip your book back, and I want you to look, actually you won't even have to flip it back. I want you to look at page 66, problem 5. Not got it problem 5, but regular got it 5. And before you do that, we're going to look at a theorem. So I want you to look in your book at the yellow box at the top of page 766. I'll bring it over here so you can see it on the screen as well. So if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. So if they tell us that AB and BC are tangents, and because they're sharing their common endpoint, then what it means is that those two segments have to be congruent. Okay? And we're going to use that to help us on what's called a circles inscribed in a polygon. So first of all, I want to remind you what inscribed means. We learned it in chapter 5, but that was kind of a nightmare chapter anyway, so it doesn't hurt to re-point it out. If a shape is inscribed in another shape, what it means is it touches it at any point it can. And so if it's inscribed, then it's understood to mean that the three sides of the triangle, or if it's a quadrilateral, doesn't matter. At the point that you say a circle is inscribed in whatever polygon it is, it automatically means all the lines are tangent. Okay? So we're going to know that as soon as you see that concept, a circle inscribed in triangle, quadrilateral, pentagon, octagon, doesn't matter what it is, we know that the two tangents that share the common endpoint are going to be congruent. So that's going to make this one crazy easy. So let's look at problem number 5. It tells us that circle O is inscribed in triangle ABC. So we know AD is going to be congruent to, line segment AD is going to be congruent to line segment AF, because they share the common endpoint A. And we know that DB, I'm not going to say it out loud, I want you to think about it. DB is going to be congruent to what line? BE. And FC is going to be congruent to EC. Okay? And so basically, kind of working our way around the circle, starting at D, it's going to be 10 centimeters plus 10 centimeters plus 8 centimeters plus 8 centimeters, should have started sooner, plus 15 centimeters plus 15 centimeters. And if you add all those together, you get, P equal. And it's kind of annoying in the book. They didn't carry the units throughout, but we know, y'all know by now, I'm pretty picky about that, so you would have to do that. So that's how you do those. I'm going to go ahead and warn you, 19 is going to be a little tricky. So when you do problem 19 on page 767, be careful with it. Okay? I think I'm not going to have time to get both of these in my 29 limit. So I am going to stop 12.1 and make a different video for 12.2. Okay, 12.2. So first of all, a little bit of a review. This is mostly stuff you've already known. Just a reminder that a radius is always from the center of the circle to the edge of the circle. And an arc is always some distance around here. I want to talk about arc BC for just a minute. So if you think about arc BC, there's two things we can do that we learned from chapter 10. The first is the measure of arc BC. Whenever you see the word measure, it's always going to be an angle, and the measure of an arc is always the same degrees as the measure of its central angle. Okay? And the length of the arc is always the fraction of the circle that it is of its circumference. So just kind of remember those two things. Now we're going to talk about something that you learned in 5th grade and 6th grade and 7th grade and 8th grade, but it didn't come up in algebra, so you may have forgotten it. That's the concept of a chord. And again, kind of like the word chemistry, the H is silent. That's because it's a Greek word, and CH usually makes the K sound in Greek words, like chemistry and chiropractor and, I don't know, probably a bunch of others. So a chord is basically any length from one point in the circle, actually let me scoot over, make sure you guys can see this, from one point in the circle to another point in the circle, and all the points on the chord are interior to the circle. So PQ is a chord. Okay. Interestingly enough, a radius is not a chord because it goes from one point of the circle, but it doesn't go to the end. But a diameter is a chord because it'll go from one point through the center to the other point, but it still meets the definition of a chord. Okay. A chord, you can also, the related arc to a chord, PQ would be a chord, and if you write it with a line above it, that's basically line segment PQ, and it's a chord because of its starting and ending points. The arc related to any chord is going to be the minor arc that the chord forms. Okay? So that gets some definitions in there. So now we'll get to our first theorems. Okay, so first of all, if you make a bunch of radiuses, a chord can always be formed by two radiuses, or radii, I guess. So OB is a radius and OA is a radius. So from the end point of the two radiuses, you could form the chord AB. Does everybody see that? So the rule is congruent central, within a circle or congruent circles, congruent central angles have congruent arcs. Actually, that's separate from the chord. But anyway, so an arc length, an arc, and a central angle are congruent. And we actually learned that back in chapter 10. Okay. This next one is the part that I thought I'd already done. Okay. So if you have two congruent arcs, then their chords are also going to be congruent to each other. So if the arcs are congruent, the line segments that form the chords are also congruent. The converse also works. If you know two chords are congruent, then you know their arcs are congruent. Okay? Okay? And so the relationship between the chord, the central angle, and the arc, they're all going to have congruent measures. Okay? So let's look at problem 2 on, first of all, you might start to panic when you see all these proofs. Again, we won't be doing proofs. I want to look at this. This is kind of messy. It says, within a circle or in congruent circles, chords equal distance from the center or centers are congruent. So you may wonder why all of this mess to show this. And this goes back to something we learned back in chapter, I want to say chapter 5, but it might have been chapter 6. The idea is the definition from a point to a line. Even though you might think that this is from the point to the line, this is from the point to the line, this is from the point to the line, the definition of the distance from a point to a line is always the distance from the point that is perpendicular to the line. It also ends up being the shortest distance. So when they draw it like this, it's just a fancy way of showing the distance from the point to a line. So if two chords are the same distance from the center, then the two chords are congruent. That's what this is saying. Also, if two chords are congruent, they're also equidistant from the center. So that's what this one says. So let's see what kind of problems we can work with that. So we're going to work problem 2 on page 773. And again, this is the one in the book. So, and these are pretty simple, but just because they're simple and they're obvious, you still have to know the rules. So it says, what is the length of RS in circle O? So they want to know this length. So let's talk about a couple things. First of all, you'll notice that these two right angle signs, what that means is that this is the distance from the point to the line because of this. And this means this is the distance from the point to the line. So we know the distance from the center of the circle to line RS is 9. And we know the distance from the center of the circle to line PR is also 9. And by theorem 12.7, we know that these two lines have to be congruent. The other thing that it shows on the marking is it tells us that this and this are congruent. You see that? These two congruent markings. So if this is 12.5, this has to be 12.5 because of these markings. So if we know that this whole thing is 25 because we can double it, and we know these two are congruent to each other. So line SR, chord SR is 25. Okay? Let's look at a whole mess of other ones that look worse than they are. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord, and if it bisects the chord, it has to bisect its arc. So if you have, it only works for diameters, it doesn't work for other chords. But if the diameter bisects the chord, if the diameter is perpendicular to the chord, then it bisects the chord. Notice the chord doesn't bisect the diameter, so it doesn't work. The converse is also true, which means this says if you know that it's perpendicular, if it's a diameter and you know it's perpendicular, you know it bisects. This one says if it's a diameter and you know it bisects, you know it's perpendicular. Okay? And kind of you put these two together, what you come up with, if you have a perpendicular bisector of a chord, and let's talk about the definition of perpendicular bisector, because that's been a hot minute since we've talked about that. If a line is a perpendicular bisector, first of all, it's of a chord. So the one that's not a chord is the perpendicular bisector, and we can tell from the picture it's a perpendicular bisector because this mark tells us it's perpendicular, and these congruent markers tell us it bisects. So we know this line bisected the chord, and we know that this line is perpendicular to the chord. Because we know both those things, it means that the chord has to contain the center of the circle, and the only chord that contains the center of a circle is a diameter. So those are those three rules. Like I said, just be glad we're not going to be doing any proofs on these. Okay? So let's take a look at a couple problems with that. We're going to do problem number 4 on page 775. So take a look at problem 4, not the got it problem, but the actual problem on 774. What is the value of each variable to the nearest tenth? And we're going to do the A problem first, and the only problem we've got is R. And R is a radius. So we're going to start by looking at it and thinking about our rules. So we know that it's perpendicular, and we know that if a line is perpendicular to a chord, it bisects the chord. So that tells us that Ln has to equal Nm. And since the whole thing is 14 centimeters, we know each of those has to be 7 centimeters. Now I'm going to focus on this triangle. I know this is 7 centimeters. They told us this was 3 centimeters. And now, crazy easy, Pythagorean theorem, we've done it a million times. A squared plus b squared equals c squared. 3 centimeters squared plus 7 centimeters squared equal r squared. 9 centimeters squared plus 49 centimeters squared equal r squared. Can't do that in my head. 57 centimeters